So this data set is covered in Unit 2, all about the two baseball players and their hits during their careers. Roger Maris had a career in the 60s to the 90s, and these were his home run hits in his 10-year career. I mean, this is more than 10 years, but I guess he didn't play in the major leagues every year. And then these were Babe Ruth's 15-year career and his home run hits. And just looking at the two baseball players, who is the better baseball player? What would you say? If that's how you define good baseball players, by the number of hits, home run hits. You know what I mean? Home run hits. So they shot the ball and they ran through all the bases to home. So that covers, you know, as far as being a baseball player, that's the best you can do, right? So for a long time, Babe Ruth held this record from the throughout the 40s and 50s, and then he was replaced in the record by Maris, who had a 61 home run hit season in the middle of his career. And then more recently, this was exceeded by a player, and I don't know who it was, but I understand that this was exceeded. So now back to this. So between the two of them, how would you defend your choice as the better or best baseball player during these, comparing these two? Who's the best? Do you think it is Maris because he got 61 home run hits? Or do you have a reason to pick Ruth instead? So the approach that I taught you, the 5 features of the distribution, should help you in making your decision and your assessment. So I go through the process in the notes and answer this question. If you make the 5 numbers, so both of these distributions, you have to make the distribution first. And that's what I do down here. I draw it. And these are the 2 distributions as a stem and leaf plot. And you can take these and stare at them. And if you do that, maybe you're still unclear. The best thing to do is make what I call a back-to-back stem and leaf plot. That way you can compare them on the same on the same number line. So let's do that. I don't know why my tablet turned inverted. You can do it like this. Okay, I'm going to show you my tablet. Actually, let me pull up the notes for Unit 2, and I'll do it there. Okay, so this is from the document called Sample Notes. Now here in the notes, my lecture notes, I actually do the 5-number summary. But let me show you first, before you do the 5-number summary, you got to make the graphs. So what I'm going to do is make the number line 0, 1, 2, 3, 4, 5, 6. So they're going to share the same stem. And I'm going to put Maris over here. And I'm going to put Ruth over here. And wait a second, let me, no, I'm going to do it like this. And I'm going to transcribe what we see there for Maris onto here. So for Maris, he has 8. So the first thing to do actually is to go here to Maris and put these numbers in order. So here they are in order. Here they are in order. And then I'm going to put them over here on the stem and leaf. So for 8, it's already there, 0, 8. And the next one is going to be, so in groups, I'm going by 10. So this is going to go from 10 to 19. So 13 will be in there. Oops, color change. 13 will be there, and 14 will be there, and 16 will be there. In the 20s, it's 23. You put it in the same line, 26 and 28. In the 30s, it's 33 and 39, and then 61 is all the way over here. So that's what I had in the sample problems document. And then over here on this side, we're going to put Ruth, but the numbers are going to, just like they ordered from the center this way, we're going to order from the center this way, or we're going to climb from the center out. So for Ruth, we put Ruth's numbers in order. No, that's not it. Here. So we're going to transcribe. So it's going to be 22, 25, 34, 35. Make sure they line up. And then 41, 41, 46, 66, 7, 9. And then we go to the 50s, 54, 54, 59, and 60. I'm going to repeat what I did last class. I'm going to smooth the distribution. This one I'm going to smooth like this, and this one I'm going to smooth like this. Now we can compare them because they're on the same timeline. And what can you say? Who is the better baseball player and why? That's the value of these pictures that we make, these graphs. What would you say? Okay, I'm going to give you guys a 10-minute break. You're going to go and look at your notes. You're going to get some water. And you're going to tell me the answer to the question and who is the better baseball player and why. Okay, so we're going to have a 10-minute break. We'll come back at 7:16. I'm going to pause the video. Have a good break. Okay, I'm back. What did you find out, or what do you think? What's your comment?
Believe has less volatility as Marvis. Marvis is more volatile.
So, okay. So that's one feature, right, of the distribution. So there's 5 features. We can talk about the features. So one was shape. What is the shape for Ruth? What are the options? Symmetric or not symmetric, or symmetric or skewed? What is what is Ruth? So you have to look at this thing here and you twist it like this. Is this symmetric? What does the curve mean again? It means if I had more data, I feel like it's going to be like that. It's just going to fill in. And even if it's, a lot more data, I can put the shape like this. It will still be like this. Can't even. So what is that? Is that symmetric or not? You can find the answer in the notes.
It's symmetric.
It's symmetric, right?
Mm-hmm.
And so I'm going to put symmetric for Ruth. And then for Maris, what do we see? What do you say?
Right skew.
Yeah, so it's not symmetric. The word for non-symmetric we're using is called skew. And there's a small observation in the high numbers, 61. One observation in the high numbers. The number line is like this. So if the tail of the distribution is in the right. So we call that right skew. So you can go step by step and say first it's skewed and skewed right. Or right skew. Why do I need that? I need that because if it's symmetric, we do things one way. If it's skewed, we do things another way. So for Ruth, it's symmetric. Number 2, what is the center if it's symmetric? It's in a big box in your notes. We discussed this last week. What is the measure of the center when a distribution is symmetric?
Median.
So if it's symmetric, the mean, the median, and the mode are all in the same place. The mode is the distribution with the peak. I mean, sorry, there's the class with the peak. The mean is the center of gravity, so it balances. And the median is the middle observation. All of those fall in this class. So they're all similar enough, but when the distribution is symmetric, we use the mean. Okay, so they're all going to be in the same class. But we measure and report the mean. For Maris, what is the center? It's right skewed, so what do we use as a center? We cannot use the mean because the mean is distorted by the value out here. When data are skewed, we use not the mode either, because the mode will be in here somewhere, because there's two peaks. Well, they're beside each other, these two classes, so it's in here somewhere. But we don't use the mean, we don't use the mode, we use the median, which is the compromise between them. So we use the median if it's skewed. So where is the center? On Maris, the center is here. It's clearly here. And on Maris, you can find the center. How do we find the median? Do you remember? There's two ways to do it. You can calculate the observation that is in the position n+1/2. In other words, you're finding the middle observation. Another way to do it is you can cross out on each side. So you go to this side and you cross out one there, and you cross out one here, you cross out one there, and you cross out one here, and you cross out one there, and you see two in the middle. You need to average 23 plus 26, divide by 2. That will give you the median. So what is 23 plus 26 divided by 2? So 24.5 is here. It's going to be in here. So right away, what do you see? You see that the expected value for Ruth is higher than the expected value for Maris. Okay, so that's an indicator that Ruth is better. Okay, so if you were to bet, you should bet on Ruth as having more hits. If they were playing around the same time in the same way, you would be better to bet on Ruth having more hits that season than Maris. So statistics in baseball are huge. Okay, people make a lot of money in baseball, in management, and gambling. And so there are a lot of statistics available to the public, and then there's some proprietary, I guess. This matters, right? Like to know who are we gonna bet on, who are we gonna invest in, who are we going to draft for our team. So they want this information. And clearly Ruth, in any given year, if they ever played in the same season, has a better expected value, better player. You can also talk about the volatility that Lucero mentioned. The volatility or the spread is the next thing. So spread for Ruth, spread for a distribution that is symmetric, you would calculate the standard deviation or the sample standard deviation. Now, you could argue that we could calculate the population standard deviation because this is all his home run hits in the season, but just his performance in the major leagues doesn't necessarily define him as the best player because he has played in other leagues and at other times. And so we'll treat this like a sample, okay? So the sample standard deviation of this data, how can we get this? How can we do this on our calculator? How do we get the sample standard deviation of this numbers? I taught you last class. So you can put those into your calculator. You remember what we did? How do I enter the data? I used the data sheet. I said second data and get the data sheet. There's something inside, so I need to clear it. Second clear work. Oh, that didn't work. Second data and then second clear work. It's clear. And I start to enter the values, 22, enter down, and it asks me for Y. I'm only entering one data set, not two variables. So I'm going to skip that and go to the second X2. I put 25, enter down, and I go past the Y, then 34, enter down, then 35, enter down, 41, enter down, 41, enter down, 46, enter down, 46, enter down, 46, enter. Is that right? Down, down. Okay, well, let me see what I have. I'm lost track now. So the first one was, wow, that's a lot of data. 22, 25, 34, 35, now 41, 41, and then 3 46s. 1, 2, 3, and then a 47. Okay. 47, enter down. 49, enter. No, not there. No. No. 49, enter down. 54, enter down. 54, enter down. And then 60. All right, let's review. So I have my data, 22, 25, 34, 35, 41, 41, 46, 3 times. 1, 2, 3, 6 times. I mean 3 times. And then 47 1 time. 49, 54 2 times. And 60. Okay, and I'm ready. Oh, no. 54, where's my 59? Yeah, I missed it. Okay, so 59 and 60. All right, so there's the data. Now I ask to show me the statistics and I scroll down, 15 observations. There's my mean, 43.93. I can put it on my document. So 43.9 or 44 hits. And that's the sample standard deviation, 11.25 or 11. We can round to number of hits. Although my rule is keep 2 more decimals than the values you entered. So you guys should practice that. You need to use your calculator for the test in 2 weeks. So practice replicating my calculations. Okay. So this one is 43.93. And S is equal to 11.25. And what is this number? That's the sample standard deviation. That's S. What is this one? Okay, so last class, okay, let me put this. So last class we talked about X bar and S. Remember, S is the square root of the variance. The variance is the average of the deviations from the mean, square deviations from the mean. Sigma, this is for the sample. Sigma is from the population. If you had the population data, you would calculate it like this. And the symbols look a little bit different. Same pattern, same pattern. This is like an average with this summing and this dividing by the total sample size. In this case, it's the sample size. In this case, it's the population size. I use a capital X because it's all the values. It's not just a sample result. So I distinguish with a capital X instead of X. And with the mean, I use the sample mean here because I don't have the population mean, but I actually have it here. So this is the Greek letter, the symbol M, sorry, the symbol for mean, which is the Greek letter M for mean. This is called mu. So what's the difference between these two measures? Which one is bigger? If I use the same data, which one is bigger? So in other words, the calculator doesn't know if we entered a sample or if we entered population data. That's why it gives you both. You have to pick. So which one do we pick? S or sigma? This is the Greek letter sigma. Or S in the Greek alphabet. So which one do we pick? This one or this one? S or sigma? I already told you we're using S. So we're using this one. But if we take sigma and use the same values, but pick sigma, the number is smaller. It will always be smaller. Okay. The reason why they use S is because it's a little bit bigger. And what we're trying to talk about is the range of the values. And we want to be sure to capture at least the majority of the values in one standard deviation. And the way to ensure that happens is they divide by n minus 1, not n. And when you divide by a smaller number, the overall number becomes bigger, goes up. So S will always be a little bit bigger to do that spread. But the formula for S comes from the formula for standard deviation, population standard deviation. All right, so let's go back to the problem. We have our mean as 44, and I'll put all this in there. Let me copy it over. Let me erase my red. And copy it over. What happened to all my stuff? Where is it? I lost my calculations. Was that a different place? Did I open a different file? I don't know what I did. I thought it was right here. Where'd it go? Hmm. So at the end, it disappeared on me. I don't know. There it is. I found it. Now, how do I make, okay, there. All right. So where were we? What was I doing? Okay, so bean X bar. Actually, I can put paste. I don't know if it's too late now because I clicked around too much. Yeah. So for Ruth, X bar was, is it too small? Can you guys see everything? Can you see my calculations?
Yes.
So we use the symbol X bar for sample mean, which is going to be 44 hits. We're just going to round it. And for S is going to be 11 hits. All right. And now we're going to do the spread for Maris. How do we do the spread for Maris when the data are skewed? We have to get the range and the 5-number summary for spread. Let me move this a little bit up. So we need to get the 5-number summary. What's the 5-number summary, Sergio? What is the 5-number summary?
I'm not sure.
Min, Q1, Q2, Q3, and the max, 5 numbers. Tell me what they are, figure them out. You guys don't have time to spare. Minimum is what? What's the smallest number for mares? What is the smallest number here? What is the smallest number here? Can you see it?
Yeah, 8.
Very good. Okay, and then what's the maximum?
61.
Great. Okay, now somebody else help him out. What is Q2? Claudia, what is Q2? Do we have Q2?
Es 50 or second quartile.
Right, so what is it? What's the value? It's right here. This is Q2. This is also the median. And this is also the 50th percentile. Okay. So what is it? 24.5 hits. Oh. So now 24.5, if we go back up here, we can do everything from here. We can do it from here. Let's do it from here for mares. So 24.5 will divide the data in 2 parts. Let me make this a little bit bigger. No, that's not possible. Let's put it over here. No, it's not possible to make it bigger. I'll take the numbers over here. So if I divide it in 2, 24.5 is here and it divides the data in half. What is the Q1? It's the middle of the first half. What number is that? What is the middle of the first half? 14 is in the middle. What's the middle of the second half? Natalia.
33.
Perfect. So that's going to be Q1 and that one's Q3 and we are done. It wasn't that hard because there were a few numbers. If we didn't have a small data set, we have to use the rule of this one here, n+1/2. And we would do it in this area and we would do it in this area where n here is 5. You put it in the formula and you get 6/2, which is 3, you see? And it's 1, 2, 3. And the same here, 1, 2, 3. It's the same rule for all 10 of them. n+1/2 will put you between these two. All right, so let's write Q1. Q1 is 14 and 33. So we get the 5-number summary, then what do we calculate? The IQR, which is the interquartile range. You have to take the third quarter minus the first quarter. What is 33 minus 14?
$19.
19. So what does this represent? This represents how spread out the data are in the middle. So you have the data, the middle point is 24.5, which is not as high as the expected value or the middle for Ruth. So this is a higher distribution, higher expected value, and less volatile as measured by S. This is more volatile by measured by the IQR, the interquartile range, which looks at the middle 15%. So from Q3, which was, what did I say, 14. So from here, 14 to 33 is known as the interquartile range, just 3 values, a small data set. But those values are the middle 50% of data. That's not 33, right? 33 is here, sorry. Let me take that away. 33. That's the middle 50%. 1, 2, 3, 4, 5, 6 observations versus 1, 2, 3, 4 observation. 14 to 33. Anyway. So anyway, so that's how we see our volatility. This is much more volatile. Sorry, this one is much more volatile, means uncertain, and it's already lower than Maris. And then we can talk about gaps and outliers as number 4. For Ruth, are there gaps and outliers? No. There are no gaps or outliers. There are no gaps. There's no extreme values on either side. So the answer here is no. Another indication that that there are no curious, uncertain, or surprising observations. Everything is rather predictable and centered around or close to the center mode or modal class. Are there gaps and outliers for Maris?
Yes.
Yes, there's gaps at 40 to 49 and 50 to 59. There's no data there. You must show that. Okay, you have, even though there's no data here, you have to show the number line and that there's gaps, because that indicates that you have something strange. It's away from everything else. That's an outlier. Then you have to test it. You have to test to see if it's actually a statistical outlier. And I showed you how to do that last class. I showed you how to do that last class, and it's in the notes. Let me just show you. I have it here, the process beginning here. And I did it here for the spending. And I did it here for another case, but I actually didn't do it here, did I? Okay, so we can do it here on this picture. Okay, so we have this picture. Let me take this drawing. So here's the box plot. Remember, Q1, Q2, 3, 4, 5 here. And what we need to do is take 1.5 boxes. So we take 1 box length and we add it here. And 1/2 of a box length. Now this drawing might not be to scale, so what we have to do is do the actual math. It's so close on my picture, but we actually have to do the math, right? So we have to do, oh, it's lining up. So we have to check. We have to take, I'm showing you the image so you understand the formula. So I'm going to take Q3 plus 1.5 times IQR And any values that are beyond or higher than that will be outliers. So what is this going to be? Let's put the numbers in. Q3 is 33 plus 1.5 times 19 that we already calculated makes what? What is that? What is 1.5 times 19 plus 33?
$61.5.
Oh, so it passes. Okay, so you get 61.5. What does it mean? What is the interpretation? So my drawing's not so bad because it just crosses here. So it means that 61 is included and 61 is not a statistical outlier. Okay, so given the range of values, given how spread out they are, 61 isn't, so unusual, but I think it's still worthy of investigation. Because it's just so borderline that you want to investigate. What would you want to investigate? Was Roger Maris using steroids, anabolic steroids during that time to improve his performance, which was at the time illegal by the rules of the American Baseball League or whatever they call it. I'm just double checking. Yeah. Okay, so it's not a statistical outlier, but it's still concerning. Any questions about my calculations? So I just illustrated to hope that you remember or understand how to use that formula. What it's doing. It's extending the regular range, the middle 50%, and saying, okay, I'm going to say you can be that far out, but just a little bit more, and it's going to be okay. Not too strange. So no statistical outlier. And it's worth investigating because it's so borderline. I like cut off my word there. Let me fix that. It's worth investigating. There's probably nothing you can do, looking back, but it would have drawn attention. It was in, the end of his career. So who knows? Maybe, it's suspicious because he did so badly in the ones before. Maybe having the years would be more informative. Be more informative so we can see how many years between. Maybe he went into training for a few years, he took a break, he healed himself because he wasn't well, and he came back strong. Here it is. Okay, no, I was looking at the ordered one, but here it was in the middle of his career, right in the middle. Yeah, the 61. All right, so now we've done this. The last one is peaks, to talk about the peaks. And it just shows you again about the volatility or the reliability of their performance. So 5 is peaks. and there's just one here, and there, I would say for Maris, there are no well-defined peaks. There's nothing really reliable. He could be anywhere. Really. It's all over the place. He could be low, he could be high, he could be down here somewhere. So no defined peaks. Peaks demonstrate predictability, and it's not very predictable. So then in my notes of the sample problems, I have all the conclusions, and I say, I'll get it out for you. Ruth's distribution reports a consistent record having an average 44 home run hits, give or take 11 seasons. Remember, that's how we use the sample standard deviation. Hold on, let me move this. Maris's distribution reveals that he has 25 home run hit a season, where 50% of the time he's hitting anywhere in the interquartile range of 15 to 33. As Ruth's average number of hits of a season is 44 hits, is higher than this range. So what I end up doing is comparing his regularity, 15 to 33, to the actual average of Ruth. The expected value is above more than like 75%, because you have the 50 in the middle, and then the 25% that goes to from the Q1 to the minimum. So Ruth's average is higher than 75% of Maris's observations. So he's just better, more reliable, better hitter. Reliably better hitter. All right. So you'll find in this document more conclusions. We did this one last class, the spending data, and with the additional comments. And then here are Newcomb's data. From Newcomb's data, I derive or develop the histograms. Okay, so how's it going? It's 8 o'clock. How is it going? Do you want me to continue? Or do you want me to leave you guys so you can get going on your review? Do you want me just to continue for another 45 minutes? Because really, me talking and you guys doing other things or not in the mood is not a good use of anybody's time. I can just stop and then you guys can review when you're more prepared to review. Everything's on the platform. What is the best use of your time? Me continuing? You have to tell me.
prefer that you continue, but I can review my own if the rest of the class wants.
Okay. Thank you. Everybody else, you want me to continue? Okay, I have 2 votes for yes, continue, and 2 abstentions.
Yeah, sure. We can keep going.
All right, so here we have Newcomb's data. And in Newcomb's data, it represents measurements that were taken hundreds of years ago. When was it? The story is told above that this was the attempt to measure the speed of light by shining a light from a high distance down to the ground. So from a far away distance to the ground below. And somebody at the ground below would take a record of the time. And with that information of when the light was shone to when it was recorded, they used that to measure the time it took for the light to transfer from one place to the other. And they did it many times because it was a physical phenomenon and they wanted to be very precise. So this is a very quick process, right? Light is very fast. So they need to take a long enough distance that they could actually see it pass. And they did it from a distance of 7,400 meters. And they found basically it takes 24,800 nanoseconds but there's some variation from the nanoseconds. So there's like, sometimes it's a little, so it's like, it's mostly in here. 2775 is like, if I use all the data. No. So this is 2775. If I just use the data up here, this is like the average, like, you know, the middle floating. Remember what the mean was, right? The mean is the value that's closest to all the points in both directions. So the mean is like 27. It's almost at 30. So it's like here. And these values were ignored. Can you explain to me, or did you read the notes? Why do we ignore these values? Why did they only look at these values up here? Not all these values. They ignored these 2 values. Sorry, not all of them. So the average was found here, ignoring these 2 values. So when we find strange values, either it was a data entry error, somebody basically wrote it down wrong or typed it in wrong. That's called a data entry error. Number 2, it could be a measurement error. Somebody actually measured it wrong. Now, in this case, it looks like a measurement error because they were recorded early on. It was around, you know, like about within 10 measurements, because these are put in order, you can see that these are the outliers here. And you could tell a story and say, aha, the first couple of measures, the research assistant or the researcher on the ground was making mistakes with the equipment, or the person who was shining the light made a mistake by recording it wrong at the moment. So it's some sort of measurement error. Early on, it never happened again. So we don't think it was like a glitch in the universe or anything. We think that probably it was just a measurement error or a data entry error, so we drop them. The third possibility is that an outlier is actually a shift, a paradigm shift, or like I said, a glitch in the system that should be accounted for, that we shouldn't just throw out. Okay, you don't just throw out data. You have to justify throwing it. You need to investigate and justify throwing it out. So for instance, Roger Maris, his outlier was considered not statistically an outlier. So we don't throw it out. We investigate it. We'll keep it because it was measured. We didn't find any evidence that he used anabolic steroids. We keep the value and use it in his data set. Okay, but in this case, we have a rationale to throw them out. So we throw it out. And then we recalculate just using this data. Got it? So that's what I explain over here. So the data is actually in the data set. I show all the data, and I think I put them in order. So these are the measures from 24,000 and some nanoseconds. Where's the Excel spreadsheet is here. So you see the data here is put in order, and you see we're going to use this data to make a frequency histogram and a relative frequency histogram. So we learned about stem and leaf plot drawings. Then we have to learn about histograms. We have to talk about what's different between the stem and leaf, what are the advantages, and what are the disadvantages of a histogram. So let me put this on my iPad. Oops, how did I lose it? How did I do that? I don't want to lose it. Here. So there are, okay, yeah, 66 observations, and is 66. So I'm going to take a picture. I'm going to put it on my iPad. Actually, no, I can just put this in the Dropbox. No, I'm going to simplify. Okay, I'm going to get it onto my iPad. I got it. Okay. Oh, no, I didn't want to do that. Hold on. No, forget that. No, I want to put it with Zoom. A little bit blurry. Or anyway, it is on mine. Okay, there's the data. Can you see it? I mean, you can follow along. Also, with the document on your side. Can you see it? Or is it blurry? Is it too small? What we're going to do is we are going to work with classes again, but now we have continuous values. We're going to work with the continuous values because I want to emphasize that we can do continuous values on a histogram. So that's another advantage, or an advantage you're going to see of histograms. So class, and then here we're going to put number of observations, and here we're going to put percentage of observations. So the first class is going to be, okay, so for n equals 64, we're going to eliminate these two. And we're going to start between 15 and go up till 20, but not including 20. Okay, because it's continuous, I need to specify if that 20 is going to be in one or another. And if I just cut it off at 20, anyway, I could do it either way, but I'm going to do it this way where it can go, the value can go up 19.9999999, in other words, but 20 is not in it. So that's what that means with the curly bracket. And then here we're going to start 20 to 25, open bracket. So this one includes 25 up to 30, but not including 30. And this one includes 30 up to 35, but not including 35. And this one includes 35 to 40, but not including 40. And this one includes 40 to 45, not including 45. No, we can stop, right? Because the maximum value, the range of observation is between 16 and 40, I think. Now start counting. How many observations between 15 and 20? Notice you can take advantage of this being 5. There's 5 here, but between 15 and 20, there's 1, 2, 3. And then for the next one, how many fall in that class? So we're grouping together the observations, but we're not writing them all down because that gets very messy with a stem and leaf. Instead, we're just going to use a bar chart for the heights, and we're just going to count the height. So how many between 20 and 25? So 5, 10, 15, 16, 17, 18. 18? Did I do it right? 5, 10, 15, 16, 17, 18. Okay, now how many between including 20? Oh, no, I'm not supposed to include 25. All right, see, I always mess that up. So everything not including 25. Do it again. So 5, 10, 11, 12, 13. I knew that number was weird. 13. Okay, the next class. So you finish it for me. Count them. Get the document, or I'll just raise this so you can see it. Oh no, I don't. Just want to raise this. So now you want to go between 25 and 30. You have to count. Not including 30. And like statistical
I
software,
think 28.
you count 28? Okay, let me see. So 5, 10, 15, 20, 25, 26, 27, 28. Yeah. So statistical software will do this automatically, but it's important to know what it's doing. So this is what it's doing. And if you do this in Excel, it takes a little time. And these are called bins, and you have to set it all up. And anyway, sometimes you want to use statistical software to do it quite quickly, even though it'll do it automatically and decide its own classes. But you can set that too. Usually you can change the settings, change the bins in Excel, or in software you can change the default how it groups things. So that's 28. What do we have left? 30 to 35. So let me erase this. And now we're going to go between 30 and 35. $13 again, right? So we have 5 and 8 is 13. Then from 35 to 40, I did it again. 35 to 40. Not including 40 is 6. And then the last one is 1. So what you do with that is you prepare what's called a frequency histogram. A frequency histogram of Newcomb's data, and you put here the bar chart, and here you put frequency or number of observations. And here you put the variable. The variable is, I guess we're going to call it time, right? Nanoseconds. And then I start from 0 if I can. If the data starts further up, you have to indicate that. So I'm going to put 5, 10, 15, 20, 25, 30, 35, 40, 45. That's enough. Let me make this bigger. I don't really need this other stuff here. So how many observations? So we're going to start at 15, right? That's how I did it. So that's going to be here to here. So from 15 to 20, how many did we say there are?
3.
How much?
3.
Oh, just 3. Okay. So let me divide up this axis as well. I have to go up to, what's the maximum number of observations? 28. So I need to make a bar height no more than 30. I'll just use 30 as a round number. So I'll call this 10, 20, and 30. This is just a sketch, right? You can do this nicely on graph paper or nicely, obviously, with Excel or software. I'm not going to make the drawings drawings are things, these sketches and things can be done. You can use a YouTube video to learn how to do this. Important part to understand is what to do. But you can easily learn to program once you know what you want. So you told me 3, right? So 3 is like about here. Oh, I went too high. So 3 is like here. Now, if there's any dispute about my scale or drawing, just going to put the number 3 in here to alleviate uncertainty about what the heck that number is. And the next one, tell me what the next one is. So the next one is 20 to 25. How many observations did we count?
13.
Okay, so again, we're going to go up with, go up here and about just about there. So we're going to call that 13. And then the next one is up to 30. How many? That's 28, right?
Yes, 28.
You can also use a ruler. I'm not using a ruler here. That's 28. And the next one is 13 again.
Yes.
And the next?
6.
So 6 is like here. It's like a little bit more. No, I went too. So 6 is like 2 of those. And that's 30 to 35, 35 to 40. And then 40 to 41 is just one observation. There we go. That's my sketch of my frequency histogram of Newcomb's data. I can smooth it out like I did before with the stem and leaf. Oops. And so what would you say is the shape of this distribution?
Symmetrical.
Right, it's symmetrical. And this, so because it's symmetrical, we use the mean, we use the standard deviation for the spread. So that's 1, 2, and 3. The 4th is gaps and outliers. No gaps, no outliers. It's very predictable. Now there can be outliers and gaps in a symmetric distribution if it's really flat and spread out, but this one there's none. And I have some example. I give you an example, all right, I think in the notes to try. So 5 is peaks and there's just one. So that's how you would summarize this or give the what's called the 5 features. So it's very predictable, around 25 to 30. So what's the difference here between this and the stem and leaf? You can use continuous values or continuous variables with a histogram, right? You don't have to remove the decimal places or round the decimal places. You can actually put continuous values here. You can have many decimal places in the data. Another difference is in the stem and leaf plot, you actually see the values. You can see 22, 23, 28. You can see the numbers. Here you don't see the numbers. You just see them combined, like grouped in classes that the similar values are put together so we can see a pattern, but we don't see the actual values. And that can present a little bit of a disadvantage because we don't see the data. Like here, for instance, all of the values, 28 values could be 25 as far as we know. We don't know because we don't see the data. Okay, so usually we have to assume the data are spread out, but that's not necessarily the case. So this can be, you'd actually need to have the data nearby to be able to manipulate or compute any other statistics. You need the actual data. At the stem and leaf, you don't because you see the numbers. So those are the main things. We like to use a histogram when you have more than 50 observations, not even, when you have many, oops. You know, I say n greater than 50, but even before that, you'd rather use a histogram. A stem and leaf is really messy. Better than stem and leaf. Any other things or thoughts about why I would do this? That took me 30 minutes. Did you understand histograms? So we get the same pattern. I mean, we analyze the pattern the same way is what I want to say. And we do the histogram when we have a lot of data, when the data are continuous. But what we lose is we don't see the actual values. Now, a slight improvement on the frequency histogram is known as the relative frequency histogram. I don't know what just happened. Okay, we're going to make a relative frequency histogram now. The relative frequency histogram comes from converting these numbers into percentages. So how do I convert to percentage? The total is 64, right? So to get the percentage, I have to actually calculate 3 out of 64. What is 3 out of 64? What percentage? Lucida, somebody's behind you.
4.7.
Somebody's at your door, I think.
Oh
Mhm.
yeah.
Okay.
Give me a second.
Okay.
But it's like 4.7%.
Okay, we're just going to round it to make it easy. We're going to say 5%. Okay. Very good. And what's 13 out of 64? Like 20%? What about 28 out of 64?
$44%.
Okay, and 13 we already have. And 6.
$9%.
And 1.
$2%.
And they sum to how much? They should sum to how much?
100.
Right, and they do. It actually works. When you round them all consistently, it should work. 100%. Okay, so if I make the relative frequency histogram, the numbers are a little bit different, but will the pattern be different? In other words, will my 5 features be different? So if I made the graph here, and I did the same thing as before, 5, 10, 15, 20, 25, 30, 35, 40. And I have a real curve in my line. Let me fix that curve. I actually have a ruler on here, but I'm being lazy. Okay, so then, so all I've changed is this, but I'm going to start at 15, 5, 10, 15, and I'm going to make 3. Oh, I need to divide up the data. So the data now goes, the highest is 44. So I'm going to divide this as 10, 20, 30, 40, and then 50 up here, right? To guide myself. And this is going to be 15. So I need the first one to be 5%. So I'm going to go halfway. Let me make it bigger for my sake. There you go. So that's going to be 5%, and I have to write 5%. Let me make it and the next one is 20 and then
20%.
44. So let me draw them all first, and then I'll put in the here. Really bad. Let me bring down the. Okay, 20 and then 44. And then 20 again. And then 9. And then 2. And I can make this big. This is 20, 44, 20, 9, and 2. And like this, I made this video, but also the video is on Moodle. And this is called a relative frequency histogram of new comms data. And I need to get some water. All right, so what is the difference between the two of them? In terms of the 5 features, is anything different?
No.
No difference in the 5 features. So we're going to have the same conclusion about it. However, we're going to have the same summary sort of statement. However, I smooth it out. I make the same sort of regular, symmetric, predictable. If I change the scale, I could actually make them look identical. I just have, different numbers spread out in a different way, and it would look identical. The difference remains that the area under this curve is going to be N, but the area under this curve is going to be what? So that in terms of the values or the percentage of observations, what is the total under the curve? But here under the curve, are the 64 observations. This relative frequency is more conventionally used in statistics because of what I can say about the tendency of observations. Remember, when I make the yellow smoothing, what am I saying? I'm acting as though I believe that this pattern will remain the same if I have all the possible data. So more data and much more data in some cases, but just if I have all the data, I believe the pattern will stay like this, and that's what the curve, the smooth curve means. So what I'm looking at here are not just the percentage of the sample, I'm actually referring to it as the percentage of the population data. In other words, these are possibilities, percentages. I can say 44% of the data are between 15, 20, 25, 30, 35, 40, 45. So I can actually say 44% of the data are between 25 and 30, which means a lot. Like almost the majority of the data are between 25 and 30. It's a very tight distribution. That's more immediately impactful and meaningful than saying to somebody 28 values were between 25 and 30, because then they'd have to ask, well, how many values were there? And they have to do a mental math to see it's 44%. Okay. So the reason I'm teaching you this about histograms, relative frequency histograms, is because the normal unit where we're going to talk, we're going to focus now, we're going to start to focus on symmetric distributions. And we're going to talk about more specifically normal distributions and then standard normal distributions. Okay, so those are 3 different things. Symmetric, normal is a subset of symmetric, and then a special kind of normal distribution is the standard normal. That's what we're going to spend next class doing. So you guys have to catch up and finish unit 1, finish unit 2, GDS, graphing and descriptive statistics. There's just a few more things you got to look at here. You're going to spend a few more hours this week. Well, I think like, depending how far you are along, 5 to 10 hours this week. And then we're going to start normal distribution next class. Try and wrap up as much as you can from unit 1, unit 2 GDS, because then you can focus on normal distribution before the test. You should actually try and start normal distribution before we meet. But if not, I'll spend 3 hours on normal. I'm not going to go back again. So make sure that you cover everything. If you need to meet with me, you have questions, I can meet you virtually. Also, before the test, the first hour and a half before the test, I'll be there to answer questions. So we're going to have an hour and a half to answer questions. And then you're going to have the test in the classroom. Okay. So let's try and move ahead. Do you have any questions right now? I want to make next week. I don't think we're going to really have time to talk too much. So try and ask me your questions before. Either, make a time to meet with me virtually and we can resolve your questions. So when we come to class, we're focused on the normal distribution and we finish it. Make sure you sleep well the night before so you're fresh. Okay. Any questions for me? So good night, everyone. I'll put up the recording so you can review it if you need. I know it's a lot of work, but it's not hard work. It's just a lot of stuff to review. This is the foundation of what we do later. The most important section is the normal section. So it's going to be important in the sense that we're going to use it till the end of the course. You're not going to see much of unit 1 again, GDS, not too much, but we're going to use the normal again and again and again. So it's a really important unit or section. Buenas noches, unless you have questions for me.
Buenas noches.
No.
Bye, thank you.
Buenas
Buenas noches.